Hello, this is Dr. Christy Patton-Lukes, Chemical Engineering Professor at Missouri S&T. In this lesson for process control, in this lesson we're continuing to look at transfer functions, but now we're going to look more closely at a block diagram and how those relate to our transfer functions. Now, a block diagram is something like you're seeing here on this front screen, and we'll be talking about that for pretty much the rest of the semester. We have our development plan, right? We define deviation variables, which is the difference between our variable and its steady state value. And then we've taken the Laplace transform. What we want to be working on now is understanding how this relates back to the original so that we don't have to take the inverse Laplace transform and we can still understand our solution. Now, what we had done in the last video is we had taken our differential equation model for a tank where we had a stream and we were modifying it by adding some pure component A to it. And we had our differential equation model in terms of deviation variables. And if we solve for x, we get this. And when we look at the effect of one input function at a time, we get these transfer functions. X of s over x1 is w bar over rho vs plus w bar, and x prime of s or x of s over w2 of s is minus 1 over rho vs plus w. Now, on these, remember that s is the variable. And that's kind of the most important thing at this moment that you need to keep in your mind. S is a variable. Everything else is a known constant value other than our two functions. What we want to do next is look at block diagrams. So for this, I have the function x1 of s, right? That was the feed composition. And if I take that and multiply by x of s over x1 of s, I get x of s. Okay. Now what I've done here is I've written what is essentially a block diagram, but it says that as I move through the block, I multiply. Okay. And I can do that here for both of ours. I've got, in terms of x1 of s, it is w over rho vs plus w. And if I'm looking at the flow rate of my stream 2, then it is negative 1 over rho vs plus w. Okay? And the actual fact is that both of these things could be changing. And so the effect of one and the effect of the other would need to be added to each other. In terms of a block diagram, I can do that by simply bringing them together and adding them to get my output function, x of s. So I multiply when I go through a block, and then I can go through an adding process where I bring both of them in and I add the result together to get my output. So that is a basic block diagram. Part of what I want you to notice here is that the denominator here is of a form something times s plus a number. I could put this into a more standard form by writing it in the form tau s plus 1. And then whatever I needed to do to get this into being a 1, so multiply or divide by something, I'll end up with a numerator of k. This is going to be my standard block diagram or block form, okay? For a first order differential equation. Okay, I had a first order differential equation. Both of these are kind of in this form. Now, what would it take for me to get it into this form? Well, I want to have a something s plus 1 instead of plus w. So let's look at this first one. If I divide the numerator and denominator by 1 over w bar, I'm going to end up with 1 over rho v over w bar s plus 1. So for x1, the k value is 1, and the tau value is rho v over w. For w2, we could do the same sort of thing, but now then k is negative 1 over w, and tau is rho v over w. Tau is the same for both, but k might not be. And another thing here is, let's think through the steps of getting this as a, taking the inverse Laplace transform. What I would need to know is what is the forcing function, okay? And let's assume, let me switch pen colors here. If I were to assume that, say, x1 of t is u of t, a unit step function, okay, then x1 of s is going to be 1 over s. All right, and if I do that, then x of s is going to be 1 over, we'll just say tau, s plus 1, and another s in the denominator. And this is going to take the form something over s and something over tau s plus 1. Okay, whatever those numbers are up there, this piece here, the first one, is going to give me a unit step function, and the second piece is going to give me a exponential decay. Well, depends on the signs, I suppose, of tau. But when you do this, you end up with that x of t, and I'll leave this to you as an exercise if you wish. I did a unit step function, so I get x bar plus 1 minus e to the negative t over tau. X prime is 1 minus e to the negative t over tau. X is that steady state value plus that 1 minus e to the negative t over tau. So this would be my solution, okay? And it does not matter exactly what my value is of tau or of k, it would just simply change the coefficients. Now, I recommend that at this step, we're going to be pausing the video, but you should go look at some of the problems that we've done earlier in the semester, where we took different Laplace transform or different differential equations and did the Laplace transform, and see if you can create the transfer functions for those. and think about general trends as we change the type of differential equation, right? First order, second order, etc. If there is some sort of forcing function on the differential equation, what does that do to the model? Okay, and play with it a little bit and see what you can learn for yourself about transfer functions. And we're going to come back and talk about these in our next lesson. Thank you very much for your time.